Hello, welcome to Basics of Finite Element Analysis Part 2. Today is the fourth day of this third week of lectures, and in the last lecture, which was yesterday, we had started discussing about approximation of geometry. So, we will extend that discussion today, and with that discussion we will introduce concepts of Jacobian and Jacobian entities and Jacobian transformation, shape functions and Lagrangian interpolation functions and some other related concepts. So, what we had mentioned in the last class is that in FEA we make two important approximations. Okay. The first approximation we make, and which we have discussed again and again, is approximation of unknown variable over an element. For instance, in a bar problem, if there is a bar which is under tension, the unknown variable will be the displacement, and this displacement is a function of x. So, example would be that over an element u of x, which is the displacement function, and we say that okay, it varies in a certain way, we assume something. So, we assume and we say that over an element it can be expressed as u I psi I x, and this is for the eth element, and I is equal to 1 to n. So, this is the approximation function. So, these are approximation functions. So, here psi I is approximation function for u, which is the unknown variable, and associated with ith node. Okay. And then ui is value of u x at ith node. And E is the eth element. And then the last thing is n minus 1, it represents order of polynomial function in psi I x. So, this is one approximation which we make, which is approximation of unknown variable. This is approximation of unknown variable. But then we make another approximation, and that is approximation of geometry. Okay. Because when we go from x domain to zeta domain, there is some transformation, and that can be also, that transformation can also be approximated, transformation from x domain to zeta domain, that can also be approximated. So, what do we do there? So, there what do we do? We say that x, so here u was a function of x, but here x itself is getting transformed. So, x is equal to summation of, so I equals 1 to m, and remember now m is a different index, here it was n, here it is m. So, there is a distinction. Okay. So, this is equal to xi. So, this is for the eth element xi superscript e times. So, here I will do a different index just to differentiate, otherwise it just generates confusion. So, instead of I am using j. So, this is jth node, and this psi is a function of zeta, where zeta is the natural coordinate. So, here psi j is Lagrangian interpolation function of order m minus 1. So, if I am summing up m parts, then the order of the function would be m minus 1, and xj is the global coordinate of ith node. So, it is not in the natural coordinate, it is the global coordinate of ith node of eth element. Okay. Now, let us call this equation A, let us call this equation B. Now, equation B, what does it represent? It represents the shape of the element, right. If I plot, it represents the shape of the element. If this is a linear element, then it will be just a straight line, the mapping will be linear. If it is a quadratic, then it will be a curve, right. So, equation B represents shape of element. Thus, these psi j functions, which are functions of zeta, and they may not be necessarily identical to these psi i's, we can make them same, but there is no rule which says that psi j and psi I are same. Okay. I could have used actually a different symbol here, maybe phi, to make it more clear. Psi I and psi j are not same, they need not be same, they can be, but they need not be same. So, psi j, these functions, psi j's are known as shape functions. They are approximation functions, but because they influence the shape of the element, they are also known as shape functions. If you call them approximation functions, that is fine, you will not be wrong, but because they influence shape of the element, they are also known as shape functions. These functions are not called shape functions, these functions psi I, because they do not influence the shape of the element, they only influence the unknown variable. So, that is why we call them interpolation functions and approximation functions. You can call these psi j's also approximation functions or interpolation functions, but they also have a special name known as shape functions, right. So, you can call these psi j's shape functions, interpolation functions, approximation functions. Psi I, you can call them approximation functions or interpolation functions, but not shape functions. So, this is important to understand. Now, I will once again say, when m is equal to 2, then x is equal to xa plus He by 2 1 plus zeta, right. So, in this case this equation and this equation become same, right, they become same, equation C and B become same. But when m is 3, this equation is not valid, this equation is valid, but then you have to construct those different shape functions using this formula and plug in there, and you will get this relation between x and psi, or x and zeta, sorry, x and zeta. So, this is important to understand. Now, we introduce this term called Jacobian. So, I will go back to our original aim. What is our original aim? To find out the integral. So, our aim I is equal to f of x dx xa to xb, right. And because we are going to do an approximate integral, strictly speaking, this equal to sign should be replaced by an approximation sign, because I am going to approximate. See, this is exact, but this will be approximated as f of zeta, right. I am sorry, it will be approximated as in terms of some interpolation functions, right. So, the moment this was exact, but if I approximate in terms of some approximation functions, then I becomes an approximate number. Now, our aim is, original aim is to do this integration, but we have said that we will rather integrate it in what limits? -1 to 1. So, we will do so aim is to do this integral, but compute this integral I in zeta domain, right. To do this, we have to do three things. We have to change limits. Whenever we do a transformation, we do three things. We have to change limits. So, xa to xb becomes -1 to 1. The second thing we do is, initially we have fx and we have to change it into f of zeta, right. So, we transform it into f of x, which is a function of zeta, or I can call it f of zeta. And then right now I am integrating it with respect to dx. Somehow I have to change dx to d zeta. So, I have to do these changes, and then I will be able to compute I in the natural coordinate system. So, what is the relationship between dx and d zeta? How do I transform that? Dx is equal to dx over d zeta times d zeta. Physically, what it means? What does dx mean physically? Dx represents a small change in x. Df means what? A small change in f. Dy means a small change in y. How small? Extremely small, infinitesimally small change. So, dx means the position is changing by a very small amount in x domain, because x represents position, right. So, dx means an absolutely small, infinitesimally small change in x. That small change in x, what is it? I can divide it by any number. So, I am dividing it by d zeta, which is a small change in zeta, and I am multiplying it by small change in zeta. That is what it means physically, right. So, this is what it is. Now, so we have to calculate this thing. If I have to change the integration parameter dx, to d zeta, this is going to come in, right. So, this has to go into this thing, and once I fit this relation here, I should know what is the value of dx over d zeta, or what is the relationship between for dx and d zeta. Now, we know that x is equal to, in general, see, for a two noded element the mapping was this thing, equation C, but general mapping is this thing. This is the general mapping, this relation, this is the general mapping, this is for two noded element only, okay. So, we will use a general mapping scheme. So, we know that x is sum of xi e psi I, and psi is a function of zeta, and I am summing it over a index I equals 1 to m, yes. So, what does this mean? dx over d zeta equals, what are xi's? They are constants, right, they are constants. So, when I do the differentiation, these are constants, these are the values of x at specific nodes, they are constants, so they do not change. So, when I do the differentiation with respect to zeta, they do not influence the differential, right. So, this is equal to sum of xi for the eth element d psi I e, and psi I is a function of zeta, I equals 1 to m. Now, this term dx by d zeta is called Jacobian of x zeta transformation. It is called Jacobian of x zeta transformation, and it can be calculated as this thing. So, this is how you can calculate it, okay. This is the Jacobian of x to zeta transformation, and you can actually calculate this. In this expression, is there anything which you do not know? Do you know size? Do we know psi functions? Psi functions do we know or we do not know? We can calculate psi from these relations. So, if this is a 3 noded element, we know psi is from here, right. So, psi's are known. What about xi's? Xi's are coordinates of nodes in the x system. So, if there is a 3 noded element, then I know what are its coordinates. So, I know xi's and I know psi. So, I can calculate d psi over d zeta and multiply it by xi, add them up, and using this approach I can calculate dx over d zeta, which is the Jacobian of x to zeta transformation. So, it is important to understand this. Here in this class we will write it as j, and because it is for eth element we can also call it j subscript e. So, dx is equal to je times d zeta. So, our original goal is to do this integration. So, now I will plug in, instead of dx I will plug in the value of d zeta. So, I integral of from xa to xb f of x dx is same as minus 1 to 1 f of x, which is a function of zeta, times dx, and dx is je times d zeta. Okay. This I can also write it as some other function g zeta, g of zeta, but g and f are not same. F, I will give you an example. Let us say f is equal to a plus bx, and x is equal to zeta square. ठीक है, x is equal to zeta square. Now, this may not be a valid interpolation function, but I am just trying to illustrate. So, what does this mean? F is equal to a plus b times zeta square, right. So, the nature of function has changed when I am expressing it in terms of zeta. So, I cannot write this as f of zeta, this is wrong. I can write it as some other function g of zeta. So, that is why I have written g of zeta, but I can write it as f of x, which is a function of zeta. This is okay, but I cannot write f directly f of zeta, that I cannot do. So, I think earlier also this is should be g. So, now in this integral, if I know the expression for g, I already know how to calculate je, then I can integrate it in the natural coordinate system and my answer will not change. Okay, my answer will not change. So, now we have developed a methodology to integrate any function in the domain x domain from xa to xb. I can do the exact integration in natural coordinate system between limits minus 1 to 1 if I have knowledge about je and if I can correctly calculate this function g. Okay. So, this concludes the discussion for today. We will continue this discussion on Jacobians and numerical integration tomorrow. Thank you.